let's learn about phase diagrams. Phase diagrams relay to us the various pressures and temperatures in which we'll have our different states of matter for a substance. So to learn about a phase diagram, let's apply water and our understanding of water. So let's choose 1 atmosphere. So at sea level, the general pressure. And let's start at a temperature at 1 atmosphere that we know water exists as a solid. So let's start at -10 degrees Celsius. Well, we know, again, we're going to have the solid state of water. That's my attempt at an ice cube. And we know that if we would increase the temperature, that will remain solid until we reach the melting point, which would happen at 0 degrees Celsius at 1 atmosphere. And then we'll keep liquid until we're roughly at 100 degrees Celsius, or until we're exactly there. And then, of course, we would begin to boil. But what if we're at pressures below 1 atmosphere or pressures above an atmosphere? Well, that's where a phase diagram can help us. And of course, what if we're dealing with a species that we're not as familiar with as water? A phase diagram always has, well, for the majority of substances, 3 quadrants that we'll look at that show us our 3 phases and the temperature and pressures in which we'll have the 3. So if I can just roughly show us what we would be seeing for water. So it's roughly like that. So anywhere within this entire region, we would encounter solid water. Here we would encounter liquid, and here we would encounter gas, which makes sense because here, high pressure, low temperature, solid. Here, high temperature, low pressure, we would just assume that would be gas. Now, we know 1 atmosphere is described as normal pressure. Okay, that's something that I'll point out in just a moment. So if you would be given any kind of coordinates, for example, what if we're given a temperature of -5 Celsius and 0.9 atmospheres? Well, then we know we're going to have water in the solid state. But what are some other portions here? Well, I'm going to go ahead and mark this as point A, point B, I'll just call this up here point C, and this we'll call this point D. All right, what if you're on one of the lines? Well, if you're on one of the lines, then you are at equilibrium between the 2 states that butt up to that line. So if you're anywhere on AB, you are in equilibrium of solid subliming to gas, while gas depositing to solid. Now, if your main phase change is sublimation, you know that because you will be increasing temperature. But if we're at a standstill, if you are just on that line, you're at equilibrium between the 2. If you would be removing heat, then we would be depositing. But if you're at a standstill, you're at equilibrium between the 2. So B and C would be equilibrium between solid, liquid, so we'd be melting and freezing. B, D would be liquid to gas, vaporizing, and then condensing. What about point B? Well, point B is called the triple point. At point B, we have all phases in equilibrium with each other. So every single phase change, we are melting and vaporizing, we are condensing and freezing, we are subliming and depositing. Extraordinary to investigate things about triple point a little further. Just absolutely fantastic, but very, very sensitive because it's a single temperature and a single pressure to be there. Point D also has a special name. Point D on our video is called the critical point. And at the critical point, there is an associated temperature and pressure. So here, whatever my temperature would be and whatever my pressure would be. I like to call the critical point the point of no return. I think based upon our common experience, we think that truly we control the phase of matter that we have only with temperature. But that's an energy cost. So it's actually more advantageous a lot to change your phases by changing your pressure. So I could possibly condense by starting with gas and then increasing the pressure on that and getting liquid. Instead of having to decrease temperature or increase temperature, I could change pressures to get my different states of matter. That often is what we're doing, of course, like in a propane tank. Propane, of course, is a gas, but as we keep filling the vessel and filling the vessel with more and more and more gas, the pressure will increase and it itself condenses. And then we purchase our propane and our butane, different tanks. But at point D, now it's really the critical temperature that really is noteworthy. Once you're past the critical temperature, you can have nothing but the gaseous state. So, nothing but gas. So we cannot change our phase once we're past here. Even if you would increase pressure, you're so energetic that you only have the gas phase. So, you might be asked for coordinates. So what phases would you have at those temperatures and pressures? But we might also be asked different questions. So if I could bring up here, if you want to pause the video, this, and it's a little more colorful than I, of course, did in pencil. This just lays out and just goes over a little bit more about the different parts of our phase diagram. But I'd like to look at some questions you might be asked if you were given a phase diagram. So here's our phase diagram. Now you automatically know that this quadrant, higher pressure, lower temperature, is where we'll encounter the solid state of this material. You also know liquid and gas. Now, could this be water? Well, there's two things to take a look at. One, the normal phase changes. So at 1 atmosphere, this substance is melting or freezing, depending upon the direction of heat input or export, at 100. Ooh, melting at 100. So this is not water. And then we're boiling at, gosh, what, like 330 or so. So no, definitely not water. But there's something else. Water is incredibly unique in that the solid state is less dense than the liquid state. And that is unique to water. So for water, this solid liquid line, this BC line for water only will have a negative slope. Only. So we can just tell here, based upon this positive slope, it's not water as well. So for water, as you increase pressure, you're actually going to liquefy from the solid state, where for most substances, of course, when you increase pressure, you are encouraging the solid state to form. Okay, so I already went through, how we would find our normal phase change temperatures. And here, for example, what is the phase of a substance at 2 atmospheres and 100? Well, if we're at 2 and then 100, we would be in the solid state for this substance. All right, but what if we were asked questions like number 8? If the quantity of this substance was at an initial pressure of 1.2 atmospheres and a temperature of 300 Celsius, and then you lower the pressure to 0.25 atmospheres. So let's get our starting point. 1.25 atm and 200 degrees Celsius. That's where we're starting. So we're starting with liquid. And then it says you're lowering to a pressure of 0.25. Do we see what we will be doing? Liquid to gas, we would be condensing. So condensation, or the liquid would be condensing. Oh my goodness, what am I saying? I'm doing the opposite. We would be boiling. Oh, Mrs. Gerhardt, we would be boiling. Liquid to gas. Oh, for crying out loud, please forgive that blunder. I guess we could generically say vaporization, but probably boiling in this case. All right. What if we tackle number 9? So we're at an initial pressure of 1 atm and a temperature of 200. So 1 atm and 200 degrees. Okay, so for number 9, that's where we're starting. And then we lower the temperature to negative 200. Lower to negative 200, well then we would be freezing. A question like number 10. If this substance was at a pressure of 2 atmospheres, at what temperature would it melt? 2 atmospheres, where would we go from solid to liquid? That would be approximately maybe 160 degrees Celsius. If this substance was at a pressure of 2, when would it boil? Oh, well, we would have to, we cannot answer with this given information. Interesting, because we could try to extrapolate, but we know that this is the condensation point. So we would just anticipate that we would boil. Cannot answer, but the best answer would be about 8-10 degrees Celsius, I would say, because that's at the critical point. And once we're beyond that, so as soon as we're greater than that, then we're going to boil. So we can't answer that with complete certainty, but we're beyond the critical point. But we're normally going to get questions more like these. Now, carbon dioxide is wonderfully unique. Okay, first off, we can see that this solid-liquid division, it has a slight positive slope, but also at 1 atmosphere. We can tell it's not water. At 1 atmosphere, we do not encounter liquid carbon dioxide. Once you're above negative 78.5 degrees Celsius at normal pressures, you have carbon dioxide gas, which of course normally we're about, 25 Celsius or so. So we just can't decrease the temperature to get liquid. What we'll have to do is get ourselves to pressures above 5 atmospheres, and then we encounter liquid carbon dioxide. So, a lot of things that can be explained to us through phase diagrams. We should expect to have to answer questions like these. Enjoy.